So the first thing we saw was this ADM Hamiltonian formulation. We saw with sketch. Of GR, and there, so we took the Einstein interaction, we introduced this ADM decomposition, so you Fourier your space-time, and then you have your lapse, your shift, and then the spatial metric. Okay. And then we saw that only the spatial components of the metric will enter the action with time derivatives, and not the shift or the lapse. That means that these two guys are, in principle, auxiliary fields. But we saw that in GR, they're actually Lagrange multipliers. So they introduce redundancy in the theory. The first class constraint, the Gates symmetry of GR. And I forgot to make contact with Juan's lecture, and is that, so in GR, we only have two properties in degrees of freedom, so tensor modes. But you don't have any property in scalar or vector. And that's why you don't generate vector during inflation. The scalar mode is sourced by the inflator field, but since you don't have any property in vector mode there, then you are not going to generate it. Okay, so that's the reason. Yeah, that's what I wanted to say. So then the second thing we saw was this treatment of the spin one field. And then, first of all, we studied the quadratic action. We wrote down a general kinetic term for the vector field and the mass. And then we saw that if we want to really describe the degrees of freedom of the spin one field, you need to make sure that you have some constraints there. So you remove one of the components of the vector field. And that led to Maxwell kinetic term. Okay? And this was fixed by this condition. And then we worked out the constraint algebra of this theory, and we saw that if you have a mass, then the constraint we impose is a second class constraint, so you stop there. Okay. But if the mass is 0, then you see that this constraint is a first class constraint, and again that means that it will introduce a redundancy in the theory, a gate symmetry, and then it will remove 2 degrees of freedom. And that's why a massive field has 3 polarizations, massless 2. I want to learn something here, but I will do it afterwards, maybe. Yes, and then the third thing we saw, right, is that coupling of these to currents. So we saw that when you want to couple this spin one field to a conserved current, to a chromatic current, this is a bit subtle because why do we want to couple it to a conserved current? I will comment on that later in the context of the spin field. But then we saw that if you couple that, then you introduce a coupling at the level of the action of this type. And this will source your electromagnetic field, your spin one field. And then we saw that we have this inconsistency of the equations, because you have the Bayesian kinetics on the left-hand side. And this is not conserved anymore, because you're introducing this new interaction. Okay, and then we saw that you can actually compute all the corrections for the by order in the coupling constant, if you want, is a charge. Okay? In this particular case, so this will give you the order Q correction, then you can compute the order Q square correction, and in this case we are lucky enough so that the series stops here. Okay? And at that order is already consistent. Of course, in Young-Mills, you have to go to fourth order, right? Yes. And the problem with GR is that it never stops, and you have to go until you get an infinite series of terms. And then we finished by convincing ourselves that the most natural way to describe the gravitational interaction is through a spin two field. Okay? And now we are going to do a similar program for the spin two field. Similar program to the one we followed with the spin one. Okay? You remember this, right? Any question about any of these points?
I have a minor comment, sorry to interrupt. That's if the gauge coupling alpha is more than 1, significantly more, it does not play any role in your expansion in Q. You said Q times Q squared and so on. The fact that the interaction is small is not crucial. It's just simply the fact that
No, it's not crucial.
you have high order terms which you have to put back in to conserve.
No, I'm saying that if this coupling constant is small, or if you're in a regime where these terms are perturbative,
Yeah.
then you can build the action order by order. Okay, of course.
So in gravity, you will find that you cannot do this expansion to all orders if the coupling is very strong. Is that right?
No, even if the coupling is small, I mean, let me go to the spin 2 case.
Okay.
Because then we will see that even if the coupling is small, you cannot stop at. Let me go because.
Okay.
But yeah, if I forget to comment on this, speak. Okay. So now let me, for simplicity, focus on the massless case, because as you all know, the massive case is much more complicated. Okay. Because you have additional complications for the spin 2 case with respect to the spin 1 when you add the mass. And you may know that this consistent theory, fully covariant theory, Lorentz and everything, for massive graviton was only built 2010. So it's been a long-standing problem. The most general one. There were some other before. Okay. Interesting. Okay, so let's write the most general Lagrangian quadratic for the field. And I'm assuming h mu is energy. Okay. Yes. Okay, so now what you do is, again, you can compute the equations of motion. So for the spin 1, we computed the conjugate momenta, and then we set pi 0 equals 0. Oh, yes, pi 0 equals 0. We could do the same here. I'm going to do it in a different way, so you can see different approaches, but it's completely equivalent. So here I'm going to compute the equations of motion. I don't know if you want me to write it down. Probably. The field equations are minus 2 the alpha h mu beta C mu h mu beta for beta plus the alpha d beta h sin t beta beta 0. Okay. And now again, we want to make some of these components non-propagative.
Second term is missing something. H. And also some indices, no? Mu mu. Second term.
That's partial.
It's partial beta over what?
Ah, yes.
There's an H missing.
Okay. Sounds good. Now we want to make some of these components non-propagative.
Mu and nu should contract each other.
Where?
Second term again. Yeah.
So that's good. Of course, I'm doing it on purpose to see if you're
We're still awake.
Okay, so now we are going to focus on the time derivatives of this equation. Okay, because now we are going to cancel the coefficient of these time derivatives, some of the components, to make sure that they don't propagate. Okay, the approach is clear, right?
Just one question. So, Brownian and Minkowski.
Yeah.
Is there a motivation for not? I mean, so we're trying, as far as I understand, to build a theory of a spin to generally covariant spin to field.
Covariant. What do you mean by covariant?
Well,
yeah. So this h mu should be a Lorentz tensor. So we want to describe the free action for a field that at the end will represent or will carry the spin 2, the massless spin 2 by representation of Lorentz. Look.
Okay. So this
So
is
that's why
theory in flat spins.
Yes.
Okay.
Yeah.
For the mode, it's not generally covariant. It's only Lorentz invariant.
Yeah, that's what I said.
Yeah.
That's right. Okay.
So yeah, that's why I was correct. Okay, so let's write it down. And for the 0, component, we get something like this. Okay, some other terms without second time derivatives. For 8 0i, look at this. Then you have this equation for the ij component plus the h minus c down here equals 0, and then you can take the trace of this equation. It's not independent, of course, and you get this plus 3 d minus c h dot 0 0 equals. Okay. So now there is a clear condition that we can impose to make one of the components non-propagating, which is A equal B. So from here, A equal B, then component doesn't propagate. Okay? This is equivalent to imposing that the shift doesn't propagate. Okay? And now, from these two, we have the trace and we have 800. You see that they are coupled. I mean, they appear in both equations. So to remove one additional degree of freedom, we need to impose that the determinant of the matrix multiplying the time derivatives of these two components vanishes. Okay? This determinant is, so yeah, something like that. And you say, plus D, 2B, minus 2C, what should be there? D minus C, plus 3, D minus C. 3D is correct. And then 3D minus A. Yes. Okay. When we solve for this, we get something like this. D equal B squared minus 2DC plus 3C squared over 2. Okay? coefficients, A equal B. This is 1, this is 1. Then this is C, and D should be given by that. Square, well, D is 1. So it's 1 and 2C. Square over 4.
Yeah, it's 1/2. Yeah, D half.
Yeah. So there was 1/2 in front. The D. That's why now I have 1/4. Okay? And with this, we're done. And then you see that we have a free parameter here. So we're obtaining a family of theories. But we should have obtained what? Yeah?
One theory.
Yes. Which one? Linearized, yeah. And we know that from Monday and Tuesday, we know that this is the theory describing spin to field, or not. So we should have obtained that. So then what's going on? Some of you probably know what is happening. We almost. Are you following so far? Yes, no? It's obvious what we are doing. Okay. So there is something that we can always do in a theory, right? And this is what? The field redefinition. I mean, if you make a field redefinition, things should be the same. And in fact, this is what is happening here. If you make this field redefinition, h mu plus alpha h times mu with h trace, then the original Lagrangian goes to the Lagrangian minus 2 alpha times 2c, this is d mu h, d mu plus, shall I write it with bases? Let me write it. So I don't bother you for it. So you get this coefficient, C, would go to C tilde, that is related to the previous ones, by C minus 2 alpha, B minus 2. And the theta.
Sure. Why do you keep B? I thought B was 1.
Yeah. It's for general.
Okay.
Times 2, and then 1. Yeah, and you keep it, so you have the general definition. Alpha plus 2 times 3 plus C times 3 alpha. Okay? And the A and B remain the same. Okay? So when you do this field definition, you are going to modify these two coefficients. Now, if you start with A equal B equal 1, then you get a relation between these two coefficients given by B tilde equal 1 times 2 C tilde plus 3 C tilde squared over 2. And the parameter that takes you from here to these new coefficients is C minus C tilde, so this should be 1. Okay? And now you see that this is precisely the relation we have here. D, we have 1/2. That's why the difference. Okay, so this is actually Fish-Pauli or linearized GR up to this filter definition. Okay. And then we can set C equals C tilde in the new frame equal 1 for normalization if you want. Well, no, it's because you start from this. So you can start from C equal 1 and then you will get that. And then here you will have 1, here, 1 for linearized GR. And the cool thing of this is that now this theory has what? A gate symmetry. Now this theory is invariant under H mu nu, going to H mu nu plus 2 the derivative, symmetric derivative of an arbitrary vector. Okay? This is linearized diffeomorphism, of course. Okay? So, is there anything peculiar here? This is the parameter I need to go from the action I obtained to this one. So what happens if C is equal 1/2? This field definition is not well defined. This is because if this is 1/2, if C is 1/2, then this field definition is not invertible, right? Because it's traceless. The new one is traceless. What happens then? Nothing, no? So to study that particular case, what we have to do is to study the theory when we set C equal 1/2. I don't know if I can write it here again.
Put it below.
That's all there. Because I mean, we obtain this for every value of C and D. Okay, so even for C equal 1, I should propagate the same number of degrees of freedom. Okay, 2 as in GR. Because yeah, I didn't say that, but these constraints I obtained will generate this gate symmetry. That's why you remove 8 degrees of freedom.
Can I ask us something?
Yes, of course.
So the problem is that C equals 1/2 regardless of A and B.
Yeah, because this field definition doesn't change A and B. It only changes C and D.
Because I wonder, A and B can always be reabsorbed in
The
the definition of H, and at this level it doesn't
Yes,
matter.
that's why I set A equal 1.
Right.
So this condition was A equal B. And now by choosing the normalization, I make A equal 1. Yes, I forgot to say that. So this problem comes from the fact that this definition is ill-defined for alpha equal 1, 4, should be right? 1 over D dimensions. This is the problem. But then we can look at this theory. Then we have here 1/2 d mu H, d mu, and here you get a factor 3 over 16 d mu A, d mu H. Okay. So this theory should also propagate 2 degrees of freedom. And this is what? It's not obvious. Right? Yeah. It's not obvious. So for this theory, we still have this symmetry. Where this is generalized. Okay? This is simply because we involve this H0i constraint. So H0i doesn't propagate. So you still have this symmetry. But then you have an additional one. Plus, okay. So this one is shared by both actions. Okay? So they're arbitrary. But then you can enlarge this symmetry either by going to full diffeomorphisms or by going to this by scale. Okay. This is what. So this is what is called peak. And this is WT, by transverse diffeomorphisms. And this is by because what is related is a linear reversion of a value scale. If you have symmetry 5. So then this is how should I? Why is it determinant? It's a value scale. It's because the determinant goes like 1 plus the trace, blah blah. And I think that's all I wanted to say about this. And there's something else. Because then we all know, right? So we should.
So when you include matter, the equations of motion for H mu,
I'm still with the fifth here.
okay,
I'm going to split matter in a moment.
will be quite different, right? In
Let me
diffeomorphism
discuss
variance
this,
and transverse diffeomorphisms.
Let me know, because what I'm going to show is that actually these two theories are the same. Up to something. Yeah, so of course, in the end, the generalization of the nonlinear extension of this theory will give you GR with full diffeomorphisms, and the extension of this will give you unimodular gravity. So you have transverse diffeomorphisms plus phi, right? But then, if you look at the equations of motion for this theory, erase the equations. Okay, so I can use this case. Well, you know, for GR, you know you can fix things equals 0, the trace equals 0, and then the equations will reduce to equals 0. Okay? The usual wave equation for this guy. This is for B. Now, for this case, you can also use this invariance to fix the trace to 0. And then, if you take the divergence of the equations, you get an equation like this. Okay? This is by taking the divergence of the equation of motion. Should I write it here? Okay. And then from here, you get that this is a constant. Okay? And from here, you get that, how should I write it? And this is 1/4 is constant x beta plus an arbitrary transverse vector. Okay? Now, I can use the transverse gauge freedom to set this to 0. By means of this information. Okay. Now, with these conditions, you can go back to the equation of motion, and they read like this. Okay? Is it the same equation? Is it?
Different equation freedom.
So this is the equation for a guy with vanishing trace and transverse. This guy is not transverse. Okay? So we are going to introduce a transverse guy that we define like this. Square delta now this is transverse, because if we take the divergence, then I have the divergence of h mu, that is given by this. Yes. So I get the divergence of this, and here I will get twice, so 1/4 of c, x beta, theta. So they will cancel, okay? So this is transverse. And now I can plug this here, and I obtain an equation of this. Okay. So now these are the equations we should compare. And you see that the difference between the two is this global degree of freedom. It's an integration constant that acts as a source. Which type of source? So again, now we are going to see that the source of this should be the energy momentum tensor. And this is the energy momentum tensor of yes. And this is this famous thing that says that the unimodular gravity is equivalent to GR, and the cosmological constant appears as an integration constant. This is the linearized version of that statement. Okay? Now, of course, at the classical level, then unimodular gravity and GR will give you the same. And now the quantum version of this thing is not settled yet. There are still arguments about it. And I guess it all boils down to the way you want to treat this global degree of freedom. I'm calling it global because it's an integration constant, not propagative. If you treat it as a degree of freedom that you need to integrate over in the path integral, well, that will give you a. I'm going to be a step here. I don't want to fight for any of those. So some people say that this could be a resolution to the cosmological constant problem because this value invariance forbids to having this operator interaction, the cosmological constant. You cannot have scales. But then some people will tell you that even if it's an integration constant, it will receive quantum corrections. But then it depends on how you define the quantum theory. And again, Raoul has a nice paper on this comment. So you can either ask him or leave and then ask him.
Since you've introduced some kind of matter, can I ask you again about matter?
That's what I'm going to explain now.
Okay, perfect. Then I'll wait.
And as usual, I'm doing like shit. Okay, so now coupling to matter. So if I want to do traditional, I would say that the natural coupling of this, or that I want to define this, such that, are you hearing me? So very much like for the spin one, we wanted the electromagnetic current to be its source. And that's what led to the full theory, interacting theory. The analogous in this case will be to impose that the source of h mu is the energy momentum tensor. So we should couple this to the energy momentum tensor of matter. Okay, so then very much like in this spin one. So you have matter action.
Is that obvious a priori?
Eh?
That the energy momentum tensor should be the source of the metric? It's not obvious.
No. But
You can have other options.
I'm going to discuss this. So if before the break I didn't satisfy you, then okay. So that's what I'm saying. If you want to follow an analogy with electromagnetism, what we did yesterday, but even there it's not obvious that the source should be there. It's because of. Okay, let's do it now. So you want to add the coupling to matter, okay? So the way you do it is h mu, t mu, and then here some constant. Okay? Now we have seen that it's crucial for the theory to propagate only 2 degrees of freedom to keep gauge invariance. Okay? As soon as you break this gauge invariance, you will introduce additional polarization. You don't want to do that. So what you do is, let's make a Gates transformation here. For the coupling terms. Now I integrate by parts, and then here I get
I'm a bit confused with the dimensions. Why m Planck and not m Planck squared?
well, this is dimension 4,
4, yes.
so this should cancel the dimension of this. Should be dimension 1. And actually,
Yeah.
very nice because this is the main problem with quantum gravity.
Mm-hmm.
Non-renormalizability. That the source has dimension 4. And then the coupling constant has dimension 1. Okay, so now if you want to keep Gates invariance, this should be 0. Okay? And that's why, I mean, this doesn't tell you that the element of tensor should be the source. But it's a good candidate. So, yeah, let's try the simplest thing, no?
A posteriori is easy, right?
Eh?
A posteriori we know because that's the method current of the reparameterization invariant, but you didn't put any reparameterization invariant.
Yeah, but it's
here.
not clear because this is, yeah, it's
Here you don't
yeah,
see
so
it.
this is the method current of time translations. So then you should couple this to the gauge field of time translation, which is not H mu, it's the feedback.
Exactly.
And then I think, this is what we were discussing, I think if you do the same with the free body information, you will end up with teleparallel gravity. But I think it never has shown this.
Interesting.
Raoul.
Yes. It's all yours.
So yeah, again, so this is the simplest thing you could do. So let's try to be traditional. I mean, let's not be modernitas. What was I saying? Yes. Okay, so you want to introduce this coupling interaction. So if you have the matter action, you have the free action, and then you have this 1 over MP, and then H mu, T mu of the free action. Okay, where T mu is defined as something. How? So let me again be conservative and use the usual prescription. But T mu you take this action, you write it in an auxiliary curved space-time. You take variation with respect to the corresponding metric. And at the end, you take the Minkowski metric. Okay? And this is nice because unlike the canonical n-elementum tensor, if you have a gate symmetry other than this one, so if you have a U1 Young symmetry, this will give you the gauge invariant n-elementum tensor. So that's why it's a nice thing to do. Okay?
So a posteriori, everything is very clear, as long as a priori. Why would you get the n-elementum tensor from the variation of the action of something that you didn't even have in the first place?
So for this,
For me, it's another current.
But you can use the canonical description of the, I mean, like using translations to define the nether current.
Without the metric, without cheat.
no, without the metric.
Yeah, that's it. It's like you have a thought theory, you
Yeah.
have translations, and then you define the nether current associated with
Okay.
translations. And then it will be equivalent to that up to identically conserved currents portions.
So you have to introduce the metric then.
No,
So
So
it's
it's
the
still the
same.
metric, whatever you add in.
no, you don't need the metric.
No?
No, this is just an auxiliary. So it's, if you want, it's a, well, it's a procedure that will give you the appropriate n-elementum tensor. And that is different from the canonical n-elementum tensor up to a boundary term, divergence. That you can always add to your current without changing the charges. Yeah. No? So you say T mu is defined up to, how do you say that? Modulo something of this form.
Superpotential.
So this is alpha, now you see, if you take the divergence of this, symmetric, this will give you 0. Okay? And again, if you compute the Lorentz generators of this guy, since it's a total divergence, when you integrate over the volume, both things will give you the same momentum, angular momentum, and all the charges. So you don't change anything here, okay? Of course, there are subtleties, and I'm going to comment on this, because now mu will be the source. So these boundary terms can have effects, but I will explain which effects. Okay, so we have this, and then, so they will be here. And then, of course, this will give you your equation of motion. Well, that's what it is. So this will give you the source. Okay? But now we have the same problem as we had with the spin one. This will have Bianchi identity. Okay? The linearized version of the divergence of the Einstein identity. Okay? This is an Bianchi identity. Is the same as we have for mass problem. Okay? This is, if we take the divergence of this gives you 0. The same here. If you take the divergence, this gives you 0. And then you get the divergence of this. But now you're introducing this interaction. So the divergence of this now will be different from 0.
Well, the thing with the 0 is the divergence of F dual, right?
F dual? What is it? Ah. No. This is the divergence of this thing.
Oh, just right.
Yeah, so it's antisymmetric. And here you have something similar. If you take the divergence of this gives you identically 0. Not on shell. Identically 0. It's an identity. And here we give you something else. So we need to correct for this. Okay? And then we need to add. Let me write this as minus 2 well, since I'm taking in the end Minkowski, I can erase it. Mu. Is it correct? Yes. No? I need to add the correction that will be, of course, part of the gamma squared. And this will be what? The variation of this with respect to the metric. Okay? This doesn't depend on the metric. So all the dependence on the metric will be here. So you will get something like h mu nu1, nu1, h mu2, nu2, and then here minus 2 squared nu1, nu1, nu2, and then at the end you take Minkowski. And this is quadratic. So if I want the correction to enter there with the correct coefficient, I need to add 2. Okay? And now you see where this is going, right? So if I continue, you see that at next order, I will get 1 over 3 factorial, 3/8, minus 2 cubed. So the full action will be on this form. Minus 2 over prime minus n, 1 over n factorial, x1, xn, h1, h mu1, mu n, and here the n variation of S0, delta g mu1, mu1, delta g mu n, mu n, and then again the volumetrics equal to Minkowski. And you see what this is, right? This is nothing but the Taylor expansion of S0 evaluated in delta mu minus 2 over n plus h mu. Do you all see this? So this is why in the minimal coupling approach procedure, what you do is you substitute the Minkowski metric by this effective metric. Effective, huh? I didn't introduce any metric here, but to define this, which is an auxiliary structure. It's not there. Okay? The reason why you obtain this is simply because you are working with spin to field, and the metric is run to a tensor. So they are somehow degenerate. Okay? You cannot do this with other fields. That's why there is this very intimate relation between gravity and geometry. And, okay. This is for the matter. Okay? But again, we have problems here. Because now, okay, you have this theory. It's not fully consistent yet. Okay? Because you will still have this issue that you need to deal with. But yeah, just for fun, I mean, if we are in the weak field limit, let's use this theory and see what happens. Okay? So now you take this theory and you work with these equations. Okay? This should be the lowest order correction to your theory. Okay? And it's okay. It's 1 over Planck mass. Okay, it will have some corrections, 1 over Planck mass squared, but it's okay. But now you go out and you measure the bending of light, the sun, and then you discover that with this theory, the angle that you obtain is like something like this, the observer. Okay, so there is something missing here. Yes. And what is missing? Is that here I'm only including the element to tensor of matter, but H medium will also have an element to tensor. So we are missing the energy from H itself. Okay? And we need to include this. And this is the tough problem to tackle. And before that, I wanted to comment on these things.
Is that obvious that you get 3/4?
Is it obvious?
Yeah.
No.
Okay.
Well, that depends on what you mean by obvious.
No.
Does it? Not to me.
Okay. Can you see from the structure of the equation that you would get
No.
a factor of
Yeah. So maybe for these PPM guys, it's obvious. For me, it's not. But it's explained in this gravity and strength, maybe. Thomas 13.
Okay.
It's explained there.
Okay.
And then, coming back to your question, here we have decided to couple to this T minimum, okay? Which is defined up to a boundary term. So what happens if we add boundary terms? So what happens is that you obtain non-linear couplings. And instead of proving that, I'm going to argue the other way around. So let's consider, so I'm going to show that this is absurd. If you consider, imagine, Maxwell, and now let's add this non-linear coupling, some scale here to the 4 here, and then here 1/2 beta, sigma, alpha beta, gamma delta, then R mu, alpha beta, this is rho alpha, rho sigma, gamma delta. Okay. This is called the double dual Riemann tensor. Okay, and I'm choosing this coupling because it's the only coupling, non-linear coupling for Maxwell field without introducing additional division of theta. Okay, this is unique. Okay, that's what I'm using it.
So what about the scale M?
Yeah?
What about the scale M?
Okay.
no idea whether it's related to Planck scale or anything.
You should. I mean, it doesn't need to.
Okay.
Now, this is different from the terms you obtain when you integrate out the fermion. Okay? You get this Riemann FF. Okay, but again, so this is an effective field theory, only valid up to the mass of the fermion you are introducing. So what I'm saying is that if you integrate out the fermion, you get terms of this type with the Riemann with some coefficients, and this will introduce you additional degrees of freedom, the ghost. But of course, this is only valid up to some scale, while this can be trusted to larger scales. If you compute the minimum tensor, this is the usual Maxwell one. I guess you all know this one. Let's write it. This is the mu squared. And now here you get a bunch of terms. Minus r, alpha, beta, gamma, delta. This is the dual. Alpha, beta, dual, gamma, delta. Plus 2, Riemann, beta, gamma, delta, F tilde, gamma, delta, F tilde, gamma, delta, plus 4 times F tilde, mu beta, F tilde, gamma. Okay? Looks horrible, I know. 2 comments. So one is that, so you see that if you have an arbitrary coupling and not this precise one, you have these 2 derivatives. Here you have 1 derivative, so you will have 3 derivatives. Okay? And what's supposed to be to do today? So that will introduce you additional degrees of freedom. In this case, no, because F tilde is identically dimensionless. So this will only act on this one, and this one only act on this one. Okay? Now the second comment is, if now you go to flat space-time, the element of tensor, this will be 0, this will be 0, but this will remain in flat space-time. Okay? But now you see that this term is precisely of the form that I wrote down here for superpotential. Remember I said that T mu is defined modulo alpha mu. Okay? And this is precisely of that form. The divergence and then the f's are antisymmetric, so it's precisely of this form. So then if you want to recover this theory with this procedure, you should take this prescription for the element tensor and add a coupling to this boundary term. Okay? And this is quite general. By choosing different boundary terms, you will generate different non-minima couplings.
So these boundary terms give rise to topological lambdas, right? The Chern-Simons lambda. You're using F duals. Isn't that right?
R dual. Well, that should be for the self-coupling of the gravity. Or you mean for the gauge field?
For the gauge field. Yeah. That's a boundary term for the gauge field, no?
No, I think no, that's minimum. FF dual. It's minimum coupling. So you don't start with this. You will start with FF dual. You follow this procedure, and at the end you see that FF dual should be formulated in this effective measure. Yeah.
But an FF dual term in 4 dimensions, it's a total derivative, and therefore
For
give rise 4 dimensions.
For the abelian field.
Even for the non-abelian, it's Chern-Simons. For the non-abelian too.
Yeah,
Chern-Simons term.
Yeah.
It is a Chern-Simons.
Yeah.
So it's a quantized number, topological number. So you would have different, you could evaluate at the boundary. You would see different windings at the boundary. So it's not a trivial thing.
No, it's not.
You cannot ignore the boundary term.
No.
Okay, fair enough. So if you accept that, that's fine.
Yeah, so boundary terms can have effects.
Okay.
I'm saying that in this procedure, in this way of constructing the coupling to matter, the non-linear couplings can be seen as couplings to these boundary terms. That's first of all. Okay, and then another thing, with this I should do this part, is that we chose the n-equal to tensor because we want to keep gauge invariance. Okay? But actually there are ways of, there are other ways of doing this. For instance, imagine you take this h mu and you couple to introduce this projector. Okay, it's not local, but let's use it. Okay, this is a transverse projector. I take the divergence, d mu. Here we have d mu. Here I have box. That simplifies with box. There are no mathematicians here, right? And then this is 0. And then you can couple h mu to some combination of let's see, mu, p mu alpha, p mu beta, plus p mu beta, p mu alpha, beta, something like this, plus some coefficients here, maybe, a, b, c, and things like that. And here, g, alpha, beta. Okay, so now this is identically conserved, this thing. And then when I perform this gauge transformation here, it will be conserved as first order already. Okay, so this is not local, but this is another way of doing this. Well, we know that the linearized Riemann tensor of metric is gauge invariant. Okay, it's like the abelian gauge field. It's like F mu. Okay. In Jack-Mills, this is covariant. But in U1, and in this case, it's exactly gauge invariant. That means that I can couple this guy to some combination. So well, this will depend on matter fields. And I guess, like this case. Okay. So here, I could write the linearized version, and this here will be fine already. I wouldn't need to resum. Okay? So you say, no, of course, you need to be careful here, because this will depend on the derivatives of h. So if you couple this to the derivatives of the matter fields, you might run into troubles, because you might add additional degrees of freedom. But if these couplings are appropriate, like in that case, it's fine. Again, so in principle you should write down everything you can. No? This is the philosophy behind quantum field theory. And well, you see that this operator, well, it depends on the dimensionality. But in principle, this operator should be, in that case, higher order operator. So this should be irrelevant with respect to the h mu t mu coupling. But you can play around with all these things. And with this, now with the coupling matter and all that, and now do you mind if we don't have a break today? Are you very tired? No, let's have 5 minutes break.
Can I ask you now? About matter?
Yeah.
Are you done with matter?
Yes.
Okay, so imagine your matter is the solar system. How would you differentiate unimodular gravity from the gravity? There's no way. So in principle, you take the equation of motion and use a source with this.
At the classical level, they're the same.
At the classical level?
Yeah, exactly the same.
Okay.
You assume conservation of the stress and tension.
Yes.
It's only the conservation we see the difference.
No. If you assume conservation, then you have no difference. Which is a natural condition, but
yeah. Yes.
Okay, so by
Everything with conditions.
doing the usual post-Newtonian tests of gravity, you cannot tell whether you have one or the other.
No, because they are.
The first order in PPN. No.
well, they have the same field equations.
Yeah, exactly the same. The only difference is that in one case, in GR, the cosmological constant is already the action,
Okay.
and in modular, it appears as an integration constant.
Right.
But at the end of the day, the field equations are exactly the same.
Well, in any case, the cosmological constant is so small in the solar system.
Yeah, that's why I'm saying.
You're not going to see the effect. Right. So when would you start seeing differences? In cosmology then? So if you don't see that in the solar system, would you see it?
Yeah. No difference.
No different whatsoever,
The only
even at
difference-
cluster
The
scale?
only difference is interpretation of the cosmological constant. In modular, there is a hope to solve the cosmological constant problem because it appears as an integration constant.
Well,
and-
you want the technical problem if you want. You don't solve the quantum problem.
No, that one. I mean, it's the same.
No, it's not the same.
What the quantum problem and the natural problem? The problem, the cosmological constant problem is that quantum corrections will typically give you corrections much larger than the value we observe. And it's not natural because there is no symmetry protecting the cosmological constant.
Right, exactly.
In principle, in unimodular, you have this valid symmetry that would protect the cosmological constant.
Right. Okay. Then we should be taught unimodular gravity in high school. Not GR. So what about at the quantum level? What degrees of freedom probability in both?
Both propagating the same. The difference is this integration constant. So, and then it depends. In the measure, so when you write the path interval, you should have propagating degrees of freedom. So here, imagine you have gauge fixed the action of that. So here you only have propagating degrees of freedom.
Transistressless.
And then here you might integrate over the cosmological constant too, if you really take it as a degree of freedom, as a global degree of freedom. While in GR, you will not, because it's not. But yeah. So this is one of the proposals.
Right, but from vial rescalings, you would be creating Filbert definitions, right? So you would also, you would always find such a term.
Yeah, so this is the paper I was mentioning by Raul. So, so that depends. Yeah, under which symmetry you want your measure to be invariant. Because typically what you do is to impose vial rescaling and full diffeomorphisms. But you cannot make much of that. But I was saying that in the measure of the path interval, you can either go to full diffeomorphisms plus vial or stick to transverse diffeomorphisms plus vial. And then there are differences between the two cases.
But there are differences because anomalies appear, or why? What are the differences?
No, you avoid anomalies.
You have all the
No, you have no anomalies.
in vial
That's it.
plus TD.
That's it.
You have no anomalies. Okay. Which you would in GR.
Yeah. If you have the tension between longitudinal diffeomorphisms and vial transformation.
Okay. Got it. Right. So it's healthier. So is it equivalent to a scalar tensor theory? No.
No, I think you can add more scalars, but in principle it shouldn't be related, so it's independent.
Okay, so now, because I'm afraid I'm not going to have enough time to talk about all the things I wanted to. So the plan is, now I should explain very briefly the Desert argument to resum the self-interactions of the graviton. The idea was to show the case of scalar gravitation because it's much simpler, and there you can really see why or how you can resum it without all the difficulties. And then, also today, I wanted to talk about instabilities in modified gravity, the types of instabilities you usually find. Swarovski theorem that has to do with these terms that give you higher equation of motion, why we always want to avoid that. And then the relation between the null energy condition and the presence of instabilities in scalar field theories. Tomorrow I wanted to talk about chameleon symmetry mechanism and Weinstein. And then some examples of modified gravity. The idea was to show the equivalence between f of r and scalar tensor, discuss a little bit Galilean theories and Horndeski, and then similar things for vector tensor theories. So you see that I was way too ambitious. So what do you want me to skip? I mean, who is interested in seeing this scalar gravitation thing? Nobody, okay.
You're quick.
Okay, you. Who would be interested in seeing this argument? For this, I must warn you that it's going to be so brief that might not be very illuminating, but I can give you the main ideas. Instabilities. Well, I guess you all know. So this idea was to show the three types of instabilities you usually find, especially in cosmology, and why they are bad and how bad they are. And then the Strogarsky theorem. I think this. Well, are you familiar with the Strogarsky theorem? You are here? No, no, no. Okay, so then I think this is something interesting to see, and it's quite brief, I would say. The relation between non energy condition and instabilities. I think this is also something interesting. But, okay. Screening mechanisms.
Instabilities with the energy conditions?
What
Kind of instabilities with the energy conditions?
either a ghost or Laplacian. So I'm going to show why you cannot violate the energy condition with a minimally coupled scalar field, or with a set of minimally coupled scalar fields. This I like. As you see, I only have like 15 minutes left for today. Okay, let's restart. Are we okay? So for scalar gravitation, so let's take the action, the Lagrangian. For scalar field with some potential, can be a master, should be fine. So then the equation of motion will be this equal 0. Okay? And now we want to couple this field to itself so that here you obtain the trace of its own energy momentum tensor. So in this case it's a bit because you don't have any need for this. Okay? It's only for illustrative purposes. But let's play the game. Okay? So then again you could add here an interaction. But then you might think that should be something like this, where this is the trace of the energy momentum tensor of this one. Okay? But this is not true. Okay? So if you do this, if you compute the equation of motion, you don't get that. You need to write down here some interaction that should be cubic in the field and with two derivatives. So something like 5, okay? And then you fix it to get here the first order correction. And then you do it order by order. In this case, it's so simple that you can plug here directly the T and see that your final action should look like this. Okay? So this is an answer. I mean, if you do it order by order, you see that you start generating a series for these two terms. Okay? That are very easy to resum because they are geometrical progression, but there is an alternative way. So let's guess that this is the final answer. So then the equation of motion will be box 5. equal minus k prime over 2k d phi square minus d prime over k. Okay, prime derivative with respect to phi. And now, if you compute the trace of the elemental tensor for this, you get minus k d phi square plus 4 d. And now you write this equation. Equal phi over m, and here minus k phi square plus 4 d. Okay? And now you compare the two. Okay? You compare the two, and then you realize that if you compare this one here, you see this is minus. So this is plus, this is minus. So k prime over 2k should be equal to 1 over m k. Right? Yes. K prime equal to minus 2 over m. And then you integrate this equation and obtain k equal 1 over 1 plus 2 phi over m, where there is an integration constant, of course, that I fix by choosing k equal 1 for phi equal 0. So I really start from this action. Okay? And now I compare the other terms. It's a bit uglier. As you can compare, you can again solve the equation. It's a first order differential equation for Q, and the solution is of course it depends on the form of the potential. Is very ugly, but then if you take a mass term, this simplifies hugely. Simplify.
Phi squared.
Okay, and then you end up with this here. 1/2. 1 over 1 plus 2 phi over n d phi square minus 1/2 n square phi square. Okay. So this is everywhere. And this satisfies that. And this is, maybe not very surprisingly, related to the massive version, if you want, of Nordstrom theory. Okay? Now let me rederive this in a different way. Are you convinced? Was it too quick? I mean, it's simple.
So if you have a different potential, lambda 5/4,
You have something else. It's not 1, it's some power of 5.
some power.
This you can solve for power of potential, but the massive cases. And it's the most natural way, right? You should start with the quadratic action and then have interactions. So this is an alternative way that I think could be useful to understand better the Desser trick, and is that let's rewrite this in the first order formalism. Okay? So you see that if you take variations with respect to pi mu, you get d phi minus equal 0. So you get the definition of the conjugate momentum. And if you take the variation with respect to this is with respect to phi, you get this, and if you use this, This is box 5. I'm taking the much less case now, for simplicity. Okay, so now again, we want to replace this equation by the trace, with the trace of its own elemental test. Okay, so for that, again, you can guess that the final action will be this one with an arbitrary function here. This is the Hamiltonian. This is the usual definition, right? Phi dot minus h. So then you can complete the equations again. In this case, you have something like this equation is replaced by this one. F prime square 0, and then mu phi minus f by mu equals 0. And then you take the from here to get the definition of phi. This one over f mu phi. You can plug it here, and you obtain again this equation that I have for that I don't have. Better? And now we want to do the same. We want to compare with the equation. So here I will get the equation for box 5. And I want to compare with the equation box 5 equal to t. Now for t, t mu is mu minus 1/2 mu pi squared. And here, one warning, because the way you compute T mu, the first order formalism, you need to make an assumption. I mean, yes. So you need to choose phi not as a scalar, but as the scalar density with weight 1, I think. And then you can promote this into a curved spacetime, and then you will get the correct T mu. Okay? This is the way you should obtain it. You should obtain the T mu in the first order formalism. Okay? I'm not going to show it, but this is crucial in tensor argument. And then, well, again, you compare the trace of these two equations, and then you get, well, let me just give you the answer. You get that F must be this. Okay? And then now if you rewrite this in the second order formalism, you recover that for the massless case. Okay? Was it too fast? I think it's easy, no?
So a posteriori, why would the scalar have to be a density?
Why?
Yeah. What does it correspond to in the GR?
Ah, yes. So now I'm going to explain the Dessler trick. Categories. So in Dessler, what we do is, what he did was to start off this action minus kappa. This is 1 over squared, something like that. And then here we introduce this. Gamma, mu, rho, and here mu. Lambda first thing to notice is that this is nothing but the
Linear
first,
Einstein.
yes,
Yeah.
the first order Einstein-Hilbert action
Yeah.
in the Palatini formalism. Okay? So here gamma is an auxiliary field. It's not the Levi-Civita connection of this, but it's an independent field, like we did on Monday. Okay? And on Monday, we saw that Einstein-Hilbert, the Palatini formalism, gives you GR. Gives you the gamma is the Levi-Civita connection of the metric. So I guess this was his main idea. That you see this and then. So here you actually have this symmetry. That one is 8, 2, and the connection changes. Okay, so you have this gate symmetry. Now, well, at this order you can compute the equations of motion for H and for gamma, and you can see that gamma is the Levi-Civita connection of this H bar at linear order. Okay? And now you plug that into the other equation, and you obtain the linearized equation for Einstein equation. Linearized Einstein tensor. Okay? So this is, that's why I explained the first order formalism for the scalar field. This is like the conjugate momentum, up to integration by parts. Conjugate momentum times the field, derivative of the field, and this would be like the Hamiltonian. Okay? And now what you do, it's a bit, I mean it's quite straightforward, but a bit long, so I will say what happens. You compute the momentum tensor of the system, and for this, you need this to be a tensorial density, like for the scalar field. So this is usually, well, not usually. Some people criticize it, but it's just the procedure to obtain the momentum tensor. And yeah, so then you compute the correction, you go kind of, okay. You compute it, and then you correct the direction with the correction. And then the correction is precisely this one. So the momentum tensor is precisely this part here. So the first order correction, corrective action, is the same. And here we have eta mu minus kappa h mu. H bar or h bar, no? Or h. Is it h or h bar?
I guess at that level it
No
doesn't
bar.
matter, no? Because if you put it or not, since mu and nu.
Okay, and now I think to
you
notice.
cancel. Doesn't matter, no? H or H bar.
Well,
Because it deviates with respect to an eta and H. So we would cancel that.
Ah, yeah.
yeah.
Yeah, doesn't matter.
Okay, but now the important thing to notice is that this correction, if you take h mu up, that's the fundamental field, this is the fundamental field, and this is an auxiliary field, this doesn't depend on the metric. You see? You don't have Minkowski metric here. So now when you write this in Kerr space-time, you will not have any metric. The only possibility would be here, in the volume element. But we are assuming that H is a weight 1 tensor. So this will cancel the volume element in the square root of minus g in the volume element.
Okay.
So at this order, we're done, after only one iteration. Okay? And this is because of the clever choice of variables. And then you can see what? This is you didn't say anything. And then you can introduce this metric minus kappa. It's per mu. And then the variant version of it, that is the root of g mu. And then the full action, again, this unit to add. This is the total derivative, okay? This is constant, so okay. You can add this to the original action, and then you see precisely that here you will have the Ricci tensor multiplied by, this is the metric, the effective metric, and here I'm adding this, eta mu minus kappa h bar mu, so it's g mu times the Ricci. So you get that the final action is precisely of a connection. And since this is equivalent to GR in the binding formalism, you obtain GR as the solution of the iterative problem. And notice that I didn't use, even though I'm using this very scientific notation, H, gamma, and all that, there is no geometrical, there is no geometry whatsoever.
I mean, the form of the action. How do you?
Yes, but this is because you.
Know generative.
Yes, but if you do this, but I'm trying to say that's why I wanted to explain the scalar field case, because this is like, so maybe not quite, but this is the way you would start to solve the problem in the first order formalism, even if you didn't know GR. Okay. But, so I agree that. And then the geometrical Riemannian structure arises. But and again, to get really deep, you need to have Riemannian terms. So this geometrical description is something useful and something beautiful, but it's not fundamental in this description. Okay?
Feynman also tried.
Yes. So there is another.
It was very iterative way.
There is another way.
I remember that one. Not this one. This one.
By the way, I'm advertising Raoul here a lot. But he also has a paper where he resums the series in the first order formalism, in the second order formalism. So you obtain all the.
The way Feynman did it, right?
No, Feynman did it by. So let me first explain how he did it.
Okay.
So he did it like I was explaining for the scalar field case. You obtain all the terms. At the end of the day, you get a recursion relation. You get some differential equations, and you solve it. Is that the way you did it? Yes. Oh. What Feynman did and others is based on the gauge symmetry. So he realized that to have a fully consistent graphene theory for the spin 2, you need to somehow promote this gauge symmetry. You need to keep it there. You cannot do it linear order, there is no way, so you have to deform it. And then you need to see how you have to deform this symmetry at a fully nonlinear order to keep, to provide a degree of freedom, even if the gravity interacts.
It was crucial that the mass was zero, right?
Yes. Yeah, because then
If
there
the
is
variance.
no. I mean, that's an interesting question, because then if you allow, because you can have, for instance, sorry, I went over time. So I finished, and now questions. No questions.
No.
So in Maxwell, yeah, so let me say this. Here I've tried to do it without using any background, in the simplest possible way. Now I would say the most natural way, or the most more modern way of seeing this is by using the representation of the Lagrange group. So you know that if you have spin 1, a nu, you have spin 1 representation that carries 3 degrees of freedom if it's massive, 2 if it's massless. The natural way of writing a theory explicitly showing Lorentz invariance is with this vector. But then there is only Lorentz invariant condition that we can write, this one. That's why for a massless vector field, there is no gauge issue. So you can just write down the action and you don't need to care. If you have a massless, then you can only remove one degree of freedom. There is no way to remove the second one by in a Lorentz invariant way. And then you can say, okay, I have a massless field, photon. I can go to a frame where the momentum looks like this, okay? And then I could try to work with only this type of thing. But this is not invariant in the Lorentz transformation. You can boost and then you generate this. Okay? So the way to resolve this is by adding a redundancy in the theory. So you don't work you don't work with a vector field, but with equivalent class of vector fields. Okay, so all the vectors differ in the gradient of a scalar will represent the same physical field. For Maxwell, so you can write mu, and this is already the gauge invariant. And now you can actually write an arbitrary function of this, and this will not spoil the gauge invariance. Okay, and so you can have this kind of interaction. For the graviton, it's exactly the same. Okay, it's not exactly the same. Why? Because for the graviton, you can write A is equal to 0 and d mu h mu nu equals 0. So this is 1, this is 4, this is 4? Yeah, 5. Okay, so I get 5 degrees of freedom. And now again, you have to work with an equivalent class, right? And now they're equivalent up to this term. But now, if you try to write this type of terms for the spin 2, it's tricky. It's more difficult. And concerning the mass, because there were some works, if you allow for a mass, you don't need to preserve the gauge invariance of. I mean, what I'm saying is that if you want to preserve the gauge invariance, all you can do is either this is equivalent to scalar tensor, or things like this. But those will introduce a ghost. So,
unless you sum appropriately and you have a boundary term.
Unless it's a constant or local. And for the massive case, this is much easier because, I don't know, I can explain this tomorrow maybe when I talk about massive gravity. So what was it? What was the question?
My question was whether having a mass changed the way you deduce
Okay.
that Lagrangian. Because you could not use the argument of gauge invariance.
Okay.
Or put it differently, can you write Lagrangian for
So the thing
a
is that
massive graviton?
If you have a mass, then this geometrical intuition that we have is somehow lost. Because for massive gravity, you really need a reference metric. That let's take Minkowski because it's maybe the most natural. And then you have Minkowski plus h mu. So somehow you have two metrics. Okay. And now it's an issue how to couple these to matter. This is a research topic. Well, now I think it's settled. Because now you can make this second metric also dynamical. You have bimetric. I don't know if you're familiar with all this. So you have bimetric, and then they can interact only through some very specific interaction terms. And now you need to tell me how these two metrics, these two fields, spin two fields, couple to matter. If only one, so if you introduce a random coupling of both fields to matters, you will spoil the structure of the interaction of the two metrics. So you will introduce a ghost. And then there are only, if you want, if the fields couple to only one metric, it's okay. But if you want both metrics to couple to the same field, then it can only happen through a very specific combination, an effective metric. But if I remember correctly, something like alpha G mu plus some root thing. Alpha delta G minus 1 A mu plus delta, something like this. So they must couple to this effective metric. Otherwise, you will spoil the structure of the graviton potential or the two metric interactions. I mean, this coefficient might not be correct, but something like that.
G and F being the two metrics.
Yes, yes. And this is because, so when you compute quantum corrections, this will give you contributions in the form of a cosmological constant or in the form of the effective potential. Otherwise, you get another interaction between the two without the proper tuning of the coefficients. Did I answer? Partially.
Partial, enough for the moment.
And, so, for tomorrow I have homework for you. And is that, oh, it's not homework, it's really nice of you if you could do this. So if you could write what you already knew about these course, these lectures, what you think was interesting, what you think it was maybe not so interesting, or I could have skipped, and ways to improve it. No, because at the end of the day, I don't know what is interesting to people or what people might like or not. Because what I find interesting doesn't need to be the same as other people find interesting.
You can get a whole variety of answers.
Yeah, but then they could converge. That could give me some idea of how to improve this. And then, tomorrow I'll go on with instabilities, just to ask. Yeah, I don't have to. Yeah, okay, I'll do what I can.